Einstein probably never told you that until the day he died. He didn't believe black holes actually existed. He even published a paper specifically in 1939, frankly stating that the black hole hypothesis lacks persuasion and could not possibly exist in the real universe. But ironically, all the evidence we have today proving the existence of black holes stems from his general theory of relativity proposed in 1915, a scientist who personally built the theoretical framework for black holes. Why would he adamantly deny their existence? This century-spanning scientific debate over whether black holes exist or not hides human space exploration's most fascinating intellectual battle. Today is your lucky day. We will break down this mystery step by step, from theoretical predictions to observational evidence, to understand how scientists ultimately confirm the existence of this cosmic abyss. Before we get into the main topic, let's start with a simple foundation. What is a black hole? Simply put, it is a celestial body with a gravitational pull so strong that not even light can escape. Just like when you throw a stone, the faster you throw it, the further it flies. But if the speed exceeds the first cosmic velocity, it can orbit the Earth. Exceeding the second cosmic velocity allows it to escape Earth, and the gravity of a black hole raises the escape velocity to the speed of light. This means that even light, traveling at 300.000 kilometers per second, once it falls into the black hole's sphere of influence, cannot escape. Therefore, we cannot see the black hole itself. We can only rely on its influence on surrounding matter to infer its existence. This sci-fi-sounding concept actually did not originate with Einstein. Instead, as early as 1784, English scientist John Michell proposed the hypothesis of dark stars, believing the universe might contain celestial bodies of massive mass from which even light could not escape. But this hypothesis lacked theoretical support at the time and was quickly forgotten. A review of the controversy, a century-long tug-of-war in the early physics community. In 1915, Einstein published the General Theory of Relativity, writing down the famous Einstein field equations. The left side of this equation describes the distribution of matter and energy, while the right side describes the curvature of space-time. Simply put, matter tells space-time how to curve, and space-time tells matter how to move. Einstein himself could not completely solve this complex equation. It wasn't until 1916, when German astronomer Karl Schwarzschild, serving on the World War I front lines, calculated the first exact solution between battles, the Schwarzschild solution. This solution predicted that when a celestial body's mass is compressed into a critical radius, it will form a singularity. Surrounding it will appear a boundary from which even light cannot escape. This is what we later called the event horizon. This critical radius is the Schwarzschild radius. According to Schwarzschild's calculations, the Sun's Schwarzschild radius is about 3 kilometers. This means that as long as the Sun is compressed into a sphere with a 6-kilometer diameter, it will become a black hole. And for the Earth to become a black hole, it would have to be compressed to just 8.7 millimeters, smaller than a glass marble. This result at the time astounded physicists. Even Einstein found it unbelievable. In his view, in the real universe, such infinitely dense celestial bodies could not exist. The Schwarzschild solution was just an abstract mathematical derivation, not something that existed in reality. In the early days, the core debate in the physics community regarding black holes centered on whether a stellar collapse would genuinely form a black hole. The mainstream view at the time believed that after a star died, some mechanism would prevent it from collapsing infinitely. For example, when a smaller mass star dies, it becomes a white dwarf, relying on electron degeneracy pressure to resist gravity. Stars with larger mass might become neutron stars, supported by neutron degeneracy pressure. Here we must mention two crucial mass limits, the Chandrasekhar limit and the Oppenheimer limit. In 1930, a young Indian physicist, Subrahmanyan Chandrasekhar, calculated and discovered that when a white dwarf's mass exceeds 1.44 times the solar mass, electron degeneracy pressure can no longer hold it up. The star will continue to collapse. This limit is known as the Chandrasekhar limit. But Arthur Eddington, a prominent figure in physics at the time, strongly opposed this conclusion. He publicly questioned it, stating nature should have some mechanism to prevent the star from behaving so absurdly. believing a star could not collapse into an infinitely small singularity. This debate lasted a long time, until later observations confirmed Chandrasekhar's correctness. In 1939, American physicist J. Robert Oppenheimer and his student Hartland Snyder further calculated and found that when a star's mass exceeds a certain critical value, even neutron degeneracy pressure cannot resist gravity. The star will continue to collapse, eventually forming a dark star from which even light cannot escape. This is what we now call a black hole. This critical mass is known as the Oppenheimer limit. The value calculated at the time was about 0.75 times the solar mass. However, the latest research suggests that this limit lies between 2 and 3 times the solar mass. This means that, under normal circumstances, any compact object with a mass exceeding 2 to 3 times the solar mass is fundamentally unlikely to be a neutron star. It is highly probable to be a black hole. However, some theories suggest if a neutron star possesses an extremely strong magnetic field, it might temporarily exceed this limit, but it will still ultimately collapse. This later provided a crucial basis for determining black holes through observations. But Oppenheimer's prediction was not accepted by the academic community at the time, because Einstein, in the same year, published a paper specifically refuting the existence of black holes. He constructed an unnatural static black hole model, arguing that as a star collapses, it rotates faster and faster, eventually rotating at the speed of light to gain infinite energy, long before forming a Schwarzschild singularity. Therefore, black holes cannot exist. Interestingly, Einstein and Oppenheimer later frequently met at the Institute for Advanced Study in Princeton, yet never discussed the topic of black holes. Up until his death in 1955, Einstein never believed in the existence of black holes. The core of this controversy was essentially a disagreement over whether the general theory of relativity was applicable under extreme conditions. Einstein believed that the laws of physics should not allow singularities of infinite density to exist. This would cause the laws of physics to break down. Meanwhile, the younger generation of physicists, represented by Oppenheimer, believed that the derivations of general relativity were rigorous when a star's mass is large enough. Collapse is inevitable. This divergence persisted for decades, until the discovery of pulsars finally brought the first crucial breakthrough to this debate. Crucial evidence: how pulsars became indirect witnesses to black holes. In 1967, British astronomer Anthony Hewish and his student Jocelyn Bell discovered a special type of celestial body. It periodically emitted stable radio pulses, acting like a lighthouse in the universe, and was thus named a pulsar. Later research confirmed that pulsars are actually rapidly rotating neutron stars. Their diameter is only a little over 10 kilometers. Yet their density is astonishingly high. The mass of 1 cubic centimeter of neutron star material exceeds 100 million tons. Due to the neutron star's extremely fast rotation and its incredibly strong magnetic field, it emits electromagnetic radiation from its magnetic poles. When the beam of radiation sweeps across Earth, we receive a periodic pulse signal. The discovery of pulsars was significant because it confirmed the existence of neutron stars. And the existence of neutron stars precisely validated the rationality of the Oppenheimer limit. More importantly, the radio signals from pulsars are extremely stable, just like a precise cosmic clock. If its orbit contains other massive celestial bodies, its pulse signal will undergo minute changes. These changes can be precisely measured by us. It is exactly this characteristic that makes pulsars an excellent probe for detecting black holes. We can imagine this process as, if a precise clock is orbiting an invisible heavy object, then the clock's timekeeping will experience a shift due to the heavy object's gravity. By measuring this shift, we can calculate the mass of this invisible heavy object. If the mass of this heavy object exceeds the Oppenheimer limit, 2 to 3 times the solar mass, and it cannot be directly observed, then it is highly likely to be a black hole. One of the most classic cases was found in the globular cluster 47 Tucani, showing evidence of an intermediate mass black hole. 47 Tucani is an ancient star cluster located 13.000 light-years away from Earth, with a history of 12 billion years. It contains thousands of stars, Astronomers found that the movement speed of stars in the central region of this cluster is unusually fast, and a large number of pulsars are distributed at locations relatively far from the center. This is completely different from the distribution patterns of stars and pulsars in clusters without black holes. Through computer simulations of stellar trajectories and comparisons with actual observational data, astronomers concluded that at the center of the 47 Tacani cluster, there exists an intermediate mass black hole with a mass of roughly 2.200 times the solar mass. This black hole acts like a cosmic spoon, stirring the surrounding stars and catapulting some stars and pulsars to further locations, thereby leaving clear traces in the observational data. More importantly, this celestial body cannot be directly observed, and its mass far exceeds the Oppenheimer limit. It cannot be a neutron star. Therefore, it became an important indirect evidence for the existence of intermediate mass black holes. Another, even more persuasive case was found by astronomers in the globular cluster NGC 1851, the PSR J0514-4002 e-pulsar system. The related research findings were published in the journal Science in 2024. This pulsar revolves around a mysterious compact object. The orbital period is 7 days, and the distance between them is only 8 million kilometers. By measuring the orbital changes of the pulsar, astronomers calculated the mass of this mysterious object to be approximately 2.35 times the solar mass, or between 2.09 and 2.71 times the solar mass. This mass perfectly falls within the mass gap between neutron stars and black holes. It is close to the upper mass limit of a neutron star and close to the lower mass limit of a black hole. It has become a strong candidate for an overweight neutron star or the smallest black hole. The significance of this discovery lies in the fact that it perfectly sits on the dividing line between neutron stars and black holes, providing direct observational support for the accuracy of the Oppenheimer limit. If this mysterious celestial body is ultimately confirmed to be a black hole, then it will be the smallest black hole discovered by humanity. Even if it is a neutron star, it has refreshed the record for the maximum mass of a known neutron star, further narrowing the mass boundary between neutron stars and black holes. Either scenario provides strong indirect corroboration for the existence of black holes. Aside from these specific cases, observations from pulsar timing arrays, PDA, have also provided broader evidence for the existence of black holes. A pulsar timing array is an observational network composed of multiple pulsars. By monitoring their pulse signals over a long period, it aims to detect the gravitational wave background in the universe. In 2023, the European Pulsar Timing Array, EPTA, in collaboration with global teams, released important clues to the existence of nanohertz gravitational waves. The signal characteristics it observed highly matched the gravitational wave background produced by the merging of supermassive black hole binaries. This implies that the universe may contain a large number of merging supermassive black holes, further confirming the universal existence of black holes. In 2025, the EPTA team won the Royal Astronomical Society's Group Achievement Award for this breakthrough progress. However, widely accepted definitive detection by the academic community still requires higher confidence evidence support. Nevertheless, whether it is the orbital observation of a single pulsar or the gravitational wave background detection by the pulsar timing array, they all belong to indirect evidence, because we haven't directly observed the black hole itself, but rather inferred its existence through its impact on surrounding matter and spacetime. To truly complete the logical loop of black hole existence, we needed to find more direct evidence. This is where gravitational waves enter the stage. Completing the logical loop, how gravitational waves provided the final verdict on the existence of black holes. What are gravitational waves? According to the general theory of relativity, whenever an object with mass accelerates, it creates ripples in spacetime, just like throwing a stone into water creates ripples. These ripples in spacetime are gravitational waves. The propagation speed of gravitational waves is the speed of light. They can pass through any matter in the universe without being absorbed or scattered. Therefore, they can carry information from the deepest parts of the universe. But detecting gravitational waves is extremely difficult. because the distortion in space-time produced by gravitational waves is incredibly small. For instance, the gravitational waves produced by the merging of two black holes, upon reaching Earth, will cause a 4-kilometer-long detector arm length to experience a change of less than 1/1.000 th of a proton's diameter. Such a microscopic change requires an extremely precise instrument to detect. It wasn't until September 14, 2015, that the LIGO Laser Interferometer Gravitational Wave Observatory, located in the United States, finally detected the first gravitational wave in human history, designated as GW150914. This gravitational wave signal came from the merger of two black holes 1.3 billion light-years away. By analyzing the waveform of the signal, scientists accurately calculated the masses of these two black holes. They were 36 times the solar mass and 29 times the solar mass, respectively. The mass of the black hole formed after the merger was 62 times the solar mass. Here is a crucial detail. The mass of both these black holes far exceeded the Oppenheimer limit of 2 to 3 times the solar mass. Therefore, they could not be neutron stars. They could only be black holes. More importantly, the gravitational waveform detected by LIGO perfectly matched the black hole merger waveform predicted by general relativity. The error was almost negligible. Why do we say gravitational waves are direct evidence for the existence of black holes? Because unlike previous indirect evidence, gravitational waves are generated by the movement of the black holes themselves. They directly carry core information such as the black hole's mass and spin. We no longer need to infer through the indirect influence on other matter, but rather, we directly heard the space-time ripples emitted when black holes merge. Just like we cannot see the wind, but we can feel its presence through the swaying of tree leaves. And gravitational waves are like the sound emitted by the black hole itself, allowing us to directly perceive its existence. The GW150914 event not only confirmed the existence of black holes, it also verified the correctness of general relativity under extreme gravitational conditions. The reason Einstein denied black holes back then was that he believed general relativity would break down at a singularity. But the gravitational wave detection results showed that general relativity still holds up under the extreme conditions of a black hole merger. This also made Einstein's general theory of relativity ultimately become the core theoretical support proving the existence of black holes. Although this is probably something Einstein himself never anticipated. Since 2015, LIGO and the Virgo Gravitational Wave Observatory in Europe have detected dozens of gravitational wave events. The vast majority of them were produced by black hole mergers. For example, the GW170104 event detected in 2017 was the merger of two black holes with masses of 31 times and 25 times the solar mass. The GW190521 event detected in 2019 was an even more dramatic merger of two black holes with masses of 85 times and 66 times the solar mass, forming an intermediate mass black hole of 142 times the solar mass. These continuous observational results formed a complete chain of evidence, basically ending the century-long debate over whether black holes exist. This made the existence of black holes a mainstream consensus in the scientific community. Some friends might ask, why don't we just take a direct photo of a black hole? Actually, astronomers have already done that. In 2019, the Event Horizon Telescope (EHT) collaboration released humanity's first photograph of a black hole. It was a photo of the supermassive black hole at the center of the M87 galaxy, with a mass of about 6.5 billion times the solar mass. This photo, by observing the radiation from the accretion disk surrounding the black hole, outlined the silhouette of the black hole's event horizon, further providing intuitive, direct proof of the black hole's existence. However, taking a picture of a black hole is extremely difficult. It requires the coordinated operation of multiple radio telescopes globally, essentially creating an Earth-sized telescope. Gravitational wave detection, on the other hand, provides us with a more universal and more direct way of detecting black holes. Conclusion: a century-spanning scientific journey of exploration. Looking back at this century-long intellectual battle over the existence of black holes, We can see the essence of scientific exploration, from controversies over theoretical predictions, to the accumulation of indirect evidence, and finally to the ultimate confirmation via direct evidence. Every step is filled with skepticism and breakthroughs. Einstein's denial back then was not because his theory was wrong, but because the existence of black holes truly exceeded the cognitive limits of that era. And subsequent scientists, through generations of observations and calculations, finally used Einstein's own theories to prove the existence of this celestial body that he always refused to believe in. From Schwarzschild's theoretical prediction in 1916 to the discovery of pulsars in 1967 bringing indirect evidence, and then to the detection of gravitational waves in 2015 completing the logical loop. This century of exploration tells us that science never fears controversy. Every piece of skepticism is a driving force for progress. The existence of black holes not only elevates our understanding of the universe to a new level, but also gives us a deeper reverence for the rigor and charm of science. Finally, I want to ask everyone, after listening to this century-long scientific debate, do you have a new understanding of black holes? If you had the opportunity to observe a black hole, what characteristic of it would you most want to know about? Feel free to share your thoughts in the comments section. If you find this science popularization helpful, save it to listen before bed. Next time you chat with friends about black holes, you'll also be able to share these fascinating scientific stories.